So in all of our videos till now, we've talked about the ionic strength, we've talked about activity coefficients, and some of what they're doing in solution. But let's focus on what's going to matter most in analytical chemistry. Usually we're going to be working at lower concentrations, where we can either try to ignore activity coefficients or at least act with them in and work with them in their fairly well-behaved region before they start having problems and you know having the numbers change, where instead of helping something dissolve and dissociate, it starts to hinder it. So we're going to stay in the regime where we don't care about the effect crashing out, basically. Now, it also means that we should think about what's going on with our most common equilibrium condition that we talk about, and that's pH. Now, what we've learned all along is that pH equals the negative log of H plus concentration. But we also learned that we shouldn't really be talking about concentration most of the time. Usually we should be talking about activity. So the real equation for this, let me just rewrite it in entirety, will be pH equals negative log of the activity of H plus. Now, we can also unpack what goes into the activity by remembering that that's actually going to be the concentration times our activity coefficient. Now let's make that a little bit more specific. Let me just go ahead and erase this and actually call it H plus. So we take the negative log of H plus times the activity coefficient. Keep these in parentheses in your mind if you're having a hard time following the order of operation for that. And that will give you the real pH. So if I start salting in with an acid, I'm expecting that I'm probably going to get the acid to dissolve and dissociate even better. Well, it was already dissolved, but it's going to dissociate even better because it's stabilized by interacting with those other charged ions. And so we're going to expect that our effective concentration, our activity, is going to have a bigger impact. So let's consider this question. What's the pH of a solution of 0.017 molar HCl that also has 0.011 molar calcium perchlorate? Well, when we woke up this morning, we would have said pH equals negative log our concentration of H plus. We know that's going to be a 1-to-1 concentration, so we can say this will be the concentration of H plus, especially since we know that's a strong acid. So 0.017. We grab our calculator, give my 0.017. I'm going to take the log of that. And of course we apply the negative sign, so we can just write that down as 1.77. Now 1.7, actually 1.770. We'll go. Now, of course, I check my sig figs and I say log. That means that I'm still in normal context. I have 2 sig figs shown. Leading whole numbers don't count once I apply a log because that's just keeping track of how many slots of my decimal points moved. These 2 are significant. This one is not. So that would be my final answer, pH of 1.77. At least that would be my final answer this morning. Now instead, my first step will be to calculate the ionic strength. My second step will be to look up my activity coefficients for each of the species. And then my third step will be solving. Okay, let's go ahead and walk through that process. We have an example problem. So we need to do our ionic strength. If you want to go ahead and just pause the video, give it a try. Okay, so the first step we want to do is we want to have each of our species. So we want H plus, we're going to have Cl minus, we're going to have Ca2 plus, and we're going to have ClO4 minus. If you didn't remember that one, calcium is 2 plus, there's 2 of them, meaning it's going to be a -1 ion. Make sure that you're still able to do that. Okay, so we have our H plus, Cl, okay, all of these ions. We're ready to go with that. We come down here to our ionic strength. So I'm going to go ahead and just put my labels over top of each of them just so that I can keep track of things. So I'm going to have 1/2 of the concentration of my H+, so I'll have 0.017 times, now it's going to be my charge squared, so +1 squared. Notice we don't really need to put in a sign since we're going to square it anyway. So we're going to have that, plus, our next one is going to be the same concentration, because I'm doing the Cl minus, times -1 squared, plus, my next species will be calcium. That's going to be 0.011 times 2 squared, plus, now we're going to do for ClO4 minus. Now we're about to write down a concentration, and we're about to make a mistake in all likelihood. I know I just made it when I was running through my practice run of this. See, my concentration here was 0.011, and I just went to town, I just started plugging in numbers. Is that really the concentration I have of each of these ions? I'll be making 1 ion of calcium, but I'll be making 2 ions here. And so this will be 0.022 for its concentration. So 0.022 times, I set up my charge, it'll be 1 squared, end of my parentheses. So I'm going to go ahead and grab my calculator, and I can calculate this out. So we'll have our 0.022 plus our 0.017 plus our 0.017. So you see I did all the easy ones first. Now we're going to do this one. Oh, okay, that's very nice of it to let me know that I've uploaded the previous video. Alright, moving right along. 0.044, because remember this is going to be 4 times that, so that one's easy enough to do in our heads, plus 0.044 gives us 0.1 divided by 2. Our ionic strength will be 0.05. Here we are. Now we need to go get our activity coefficients. We'll need one for H+, we'll need one for Cl-, we'll need one for Ca2+, and we'll need one for ClO4- if we're going to do things with all of them. But remember, the last thing that we're going to do is just measuring pH, meaning this is going to be the only one I actually have to work with for the moment. So we need our activity coefficient for H+ at 0.05 ionic strength. So we come to our activity coefficient table, we find H+, we come across to 0.05 for ionic strength, and we find activity coefficient to be 0.86. So we have activity coefficient is 0.86. We're going to go ahead and set things up. Our pH equals negative log. I could have just gone ahead and solved for activity first, or I can go ahead and just plug things in right now. So I have my 0.86 activity coefficient times my concentration of H+ right up here. So I have 0.017 molar. And now I'm set to go. I grab the calculator again. So 0.86 times 0.017 gives me that value. Now I take log of that. You can see that I'll end up with, once I apply the negative sign to that, I'll have 1.835. So 1.835 should be my pH. Again, we do our sig figs. We had 2 sig figs here. This doesn't count because I took a log. These 2 do count. That one doesn't. Now that means I probably should retain an extra place to decide which way to round that 5. The value right after the 5 is a 0, but there's lots more places of information that I know. If it didn't have any information, I'd have to round to the even number, so it'd be 1.84. I have lots more information, so I look at it and I say, okay, yep, it's slightly above the 5, so I'm still going to go to 1.84 for the pH. So final answer, 1.84 pH. Now you can see that that's different than the 1.77 that we would have done if we had just woken up this morning and hadn't thought through what goes on with our activity coefficients. We always want to make sure that we handle our problem to completion as best as possible. Now that said, you can see that realistically speaking, in the grand scheme of things, pHs, we usually don't care about an exact pH. It's just not something that's experimentally critical to us on a lot of cases. And so you can see that getting to a pH of 1.8 without activity coefficient and a pH of 1.8 with activity coefficients, you can see that it would still give us the same overall measurement as long as we are being kind of crude about it. That's why oftentimes you'll see that we're going to neglect activity coefficients in our pH calculations, but we should never forget that that's what's actually going on.